Right, so in this video, we're going to be covering question 8 of the Fall 2016 final. And the question asks you to indicate whether the following statements are true or false and briefly justify your answer. So if false, a counterexample is also sufficient justification. Starting with part A, right, our statement is if all edge weights are equal and positive, breadth first search starting from node A will return the shortest path from a node A to a target node B. And so let's really quickly just take a look at an example. Let's say that this right here is our graph, and all of the edge weights are some equal and positive edge weight W. Right. So in this case, how can we represent any path length from A to B? Let's take a look at this path highlighted in green. And so we can say that this path would have length 3W, right? Because we have 3 edges, and each of them has weight W. And so we can generalize this to any path to say that the path length for any path from A to B is equal to W times the number of edges in the path, right? And so what does breadth first search do, right? When we're looking at breadth first search, we're going to consider vertices in order of number of edges from A, right? If we start our breadth first search from A. So for example, if we start our breadth first search at A, we'll first look here, and then we'll look at all vertices one level away or one edge away. And then we'll look at all vertices 2 edges away, for example, here and here. Right, and so the path that is output from breadth first search is going to be the path that has the least number of edges. So BFS gives path with least number of edges. And so hopefully at this point, we kind of see a correlation between the two, right? We see that BFS gives us a path with the least number of edges, and we can express the path length or the distance going along some path as W times the number of edges in the path. And so if BFS gives us the least number of edges, or a path with the least number of edges, then the path length in our graph where all the weights are equal and positive will also have the shortest distance. And so in this case, we say that this is going to be true. Right, moving on to part B, the statement for part B is if all edges have distinct weights, the shortest path between any 2 vertices is unique. And so in this case, we'll find that it's false. And let's come up with a counterexample. Right. Let's say that we have this graph on the right with 4 vertices A, B, C, and D. And let's say we're trying to find the shortest path from A and ending at D. So here there are 2 paths that we can take. We can either go from A to B and then B to D, or we can go from A to C and then C to D. And so let's try to find a combination of edges with distinct weights such that the shortest path between, or the shortest path can be either of these 2 paths, right? Here or here. And so we can try a couple of numbers, but we'll find that one example that works is setting these to 1 and 4, and then these to 2 and 3, right? Because if we take a look at what the path length for either of these paths are, they're both 5, right? So either of them is considered the shortest path. Now let's look at question C. Right, so this question says, assume we have some graph G with a unique shortest path from vertex A to vertex B. We add a positive constant K to every edge to create a new graph G prime. And so the shortest path in G prime from A to B is the same in G prime as in G. And so we don't know whether this is true or false just yet, but let's start taking a look at how our path lengths are going to be affected by adding this positive constant K. And so in G, let's just say we have some path. We aren't looking at any specific example yet, but let's just say we have a path from A to B that has length D. Right? How is this path length going to be affected when we add a positive constant K to every edge to create G prime? Well, in G prime, the path length should be D plus K times the number of edges in the path. And the reason for that is because if every edge weight has its is increased by a positive constant k, and there are some number of edges within the path, then all of them will be increased by k, and the entire path length will be increased by k times the number of edges. And so from this equation, you might be able to see that the path lengths increase differently based on how many edges are in a given path. So you might imagine that if we have some path in G that has very low weights, but a lot of edges, then it'll be affected more when we create G prime than some path that might have a really large weight originally, but only a single edge, for example. And so let's make that a little bit more concrete using this example here. Let's say we have this graph G that has 3 vertices A, B, and C, and we want to find the different paths from A to B, right? And so one path takes 2 edges, while the other path only takes 1. And so it's still possible in graph G for the 2-edge path to be shorter than the 1-edge path, right? Because, for example, if we make these 2 edges equal to 1, and then this edge weight equal to 3, it's shorter to go A to C than C to B, right? But what happens if we go from G to G prime? By adding some constant k, which is equal to 2, right? If we add k is equal to 2, the edge weights become 3, 3, and 5. And we'll see that because this path here was affected more by adding an edge weight of k to each of the edges, our new shortest path is taking the direct path from A to B. And so at this point, we found a counterexample for part C, where the path length does change between the path does change between G and G prime. Right. Last up, we have part D, which is looking at topological sorts. So it says that topologically sorting a connected graph with E edges requires big theta of E log E time in the worst case. As a refresher for what topological sort is, right, the goal of topological sorting is to order the vertices such that all edges go from an earlier to a later vertex in the order. And so in class, we saw two different algorithms. And so I'll go through one of them here, but just know that both of them have the same runtime. And so in this case, our first algorithm said that we're going to reverse the graph, which means basically for every single edge, we're going to switch the direction. And then we're going to compute the post-order traversal on the reversed graph. And so we see this step here. And so the post-order traversal should output some order where the edges in the forward graph are going from like earlier edges or earlier vertices to later vertices. And so just really briefly, intuitively, why this works is because when we compute the post-order traversal, we're going to have to visit every single one of the children before ever visiting the vertex itself, right? And so if we apply a post-order traversal of the reverse graph, this means that we're always looking at the children before ever looking at the vertex itself. And so when we look at the forward graph again, this means that we're always going to place the vertices that are ancestors of a given vertex in the post order before ever placing that vertex into the post order, right? And so if we place all the ancestors into the order before ever placing the given vertex there, then this will be a valid topological sorted order because we must have all the ancestors in the order before the given vertex. Right? And so now let's actually look at the runtime of this topological sort algorithm. Right? Our first step is going to be reversing the graph. And so one way of just reversing the graph is, let's just say we traverse every single vertex, and then for every graph, we switch its direction. Right? And so what's the runtime of this step? This is going to be big theta of V plus E, right? Because we have to look at every vertex once, and we also have to look at every edge once. And so now, how do we compute the post-order traversal of the reverse graph? Well, this can be done with DFS. Right? And so if this is done with DFS on a reverse graph, which has the same number of vertices and edges as the forward graph, right? This will also take the same runtime as DFS, which is big theta of V plus E. And so hopefully you can see at this point that we have two steps, both of which are taking big theta V plus E runtime. And so this is not in the worst case big theta of E log E. And as a result, we can say that this part is also a false statement.